Another draft physics video presentation. Oh, microphone. Oh, sorry about that noise. Happens and such. No, happens here anyway. So, Van Biezen photons. We'll talk about photons. See where it goes.
Line. Now we're going to try and tackle the concept of how big a photon is. And unfortunately, it's going to be very difficult, probably impossible, to come up with some means of describing the size of a photon.
Right. So, I mean, they've had hundreds of years to work on this, sort of, with some sort of models, maybe only 100 years plus, with some idea of electrons and protons. Yeah, chair. Being the cause, somehow being the conduit, catalyst for the creation of a photon. And so they haven't really dealt with most of, let's say, that's good enough. The idea of what this vibration is. So they want to call it a wave or a vibration. I guess you could say that it's clearly vibrating, the material it goes through, that when you heat something, you create photons. So that sort of is a clue that it has something to do with how much moving stuff is doing. And I guess I would argue that they have this idea that it moves without being moved. Like there's no mover for the movement. So they sort of have this idea that once something's moving, I don't know exactly how to draw this idea of a vibration, but you could sort of understand that if I have something on a stick and I vibrate it and it goes back and forth, that it's the stick, okay, that's making it vibrate. That it's bending, and then that's creating a kind of a new kind of potential energy, in the sense that it's resisting, it's compressing it, it's pressurizing it, and it's going to release the pressure back in the opposite direction. And so the stick is really doing the vibrating, and the thing is just a victim of being on the stick. And so for a conversation about photons, you really don't have any stick. Okay, so all you really have is electrons and protons, and the understanding that they have a connection to each other, tension that's also based on movement. Okay, if one moves, the other moves because there's a change in the pressure. So I could argue that if I don't know if yellow is exactly visible. No, it's not much of a distinction. So I guess we could make this blue-ish. Well, that's a little better. So that an electron and proton, if the electron moves, it could sort of be understood that that creates a distance between the electron and proton, and whether you think it's a pull force or push or whatever. The fact is that there's going to be the cause, the effect of that is to move the proton into that evacuated space. And in a sense, the resistance to that movement is just the resistance of leaving a low pressure. And the reason why you would leave the low pressure is because the low pressure became high for a moment. So you could sort of argue that when electricity goes into a wire or something, that it's pushing electrons. So there's a bunch of stuff that goes in, and the electrons get pushed and they vibrate, so to speak. They move in one direction, and that there's going to be some action that's going to cause them to move back in this direction. And how much you can get out of that, like how much of a stick that really is part of the question, I suppose, in terms of what's creating the photon. Now, I would argue that there's no free lunch, so nothing can move without you being able to dissect. Should turn the other light on. Why it's moving. It has to do something. So I would argue for the electron to move, it has to absorb a force in the direction. That is, the force has to push it. Something has to exchange with it for it to be possible for it to move in a direction. There has to be momentum The momentum has to move it. And likewise, when it stops, so if this electron is moving, what's going to stop it is, well, yes, this connection it has between the electron and the proton, and the fact that there's energy coming from the external world, pressure, that's also going to stop it. And the catch, as I would say, the what's really going to happen is you've given something motion in a direction by pushing pressure in. And just like sort of the ground, you can get the idea that when you push pressure into the ground, if I try to poke a hole into the ground, it doesn't just push back up, okay? The sides push, and the hole would collapse. So if I try to dig a really deep well, the sides of it will come crashing in if I don't put something in there to prevent that from happening, to fight against that pressure. And so it's the same thing, I would say, for like an antenna or heat. You pump it in, and the only way it can express itself, you're pumping it into a container, and the idea is that once it's in the container, it's in the container. And the idea is, it doesn't matter whether it comes out here, it comes out here, it doesn't matter which way it comes out, it's going to come out of the surface. That's the only place it has to get out, is the surface. And that when these surfaces are doing this, electrons are going out and in and out and in and out and in and out and in, vibrating. And what's happening is they're making an exchange with the external energy, in the sense that they have energy going this way from the energy you pumped in. They're going to make an exchange in the electron, and the electron, instead of having this, it's going to lose this back to the environment, and it's going to absorb this bit of energy. And that this is your frequency. That this is the element of your photon. This is a piece of it, or a node in the mechanism. And that as long as you keep pushing these electrons at a consistent rate, they'll keep collapsing back into the material at a consistent rate, and then the collapse back into the material is essentially this exchange of an arrow. And then if they do that at a frequency, at a reliable rate based on the pressure, then you'll end up with this constant exchange. So if you think about it like heat in a box, the exterior of the box, the interior of the box is constantly applying this pressure at a rate, because there's little bits in here bouncing around, and there's an average rate that they hit one of these surfaces, and that average rate gets revealed on the surface by a bunch of electrons being in the same condition at the same time, and then making their exchanges from the same place in space, essentially. So another way to think about it is that what you're basically doing is taking a surface and moving it. So it's, the surface is here, you're going to move it out and then move it back in, and then move it out and move it back in, and it's in a medium in the sense that there's energy on the exterior coming from the outside world, and you're providing energy going out in the form of the electrons, and the electrons are going to make the exchange of converting their motion back into these arrows. So they're going to push this stuff back out, and you can sort of understand, as I'm moving the surface in a medium like water, that's how you make waves. And so the light is being created by the same kind of mechanism, in the sense that there's a physical stuff is moving in a direction, and the tension of the medium, this, is going to push back in a sense, and there's going to be created a change in pressure based on that. So you can sort of understand that there's less pressure to the exterior world if I'm running away from it. It can't hit me. If I'm running away from a force that's coming at me, a bullet, it's going to hit me at a later time than if I'm not running away from it. Okay, if I'm running towards it, I'm going to get hit sooner. If I'm running away from it, I'm going to hit later. And so you end up having this reflection, okay, that's going to be happening at the rate, okay, that these electrons are being pressurized. More pressure, the faster the rate. Less pressure, the lower the rate. based on just the laws of averages, average temperature kind of thing. So in a sense, electricity is temperature, in a sense. All right, that's probably just enough food for thought. So, this specific subject is size, and as pointed out, the consistency, the surface, how this surface moves, like this, the surface isn't this giant hand, for example, especially metals. It's just a bunch of collections of atoms, and mostly in what are called crystals. So most of the objects that create heat or light readily are substances that are crystals in terms of how the chemistry is lining up, how the atoms arrange themselves. So it's not a one atom event. It ends up being a bunch of atoms, okay, that are doing things that are absorbing the energy and moving as a collection. So just like I could make a car out of Play-Doh and I could push on it, and I don't, I just push and my hand goes inside the car. A crystal means that the atoms don't allow that to happen. One atom doesn't move, they spread it very quickly, like conductors especially. They spread the pressure very quickly. So any pressure in ends up being pressure on more than one. So any collection of momentum ends up being a collection that moves the whole object, the whole crystal. And then the whole crystal moves back. And by whole crystal, I just mean that the electrons and protons are tightly, are strongly pressurized, held together by a lot of tension. So they just really won't move until you move all of them. And then you have to move all of them back. So a photon is something a collection of atoms creates. And I sort of made this argument before. I think it's a strong argument for the real function of, how you can understand the, how the energy is dissipated through a substance. But the argument was there was two kinds of polarization that you could really talk about when you're talking about electromagnetic radiation. Oh, stop it. Do have to get some new technology one of these days. Anyway, polarization, and the curious thing is that both things have polarization, like a radio wave and photons. You can talk about their polarization, but one is caused by something kind of obvious, okay, which is antenna polarization. So if I'm doing the radio wave thing, and the idea is to, make a light source that's visible, so I put it high in the air, so everybody can see the lighthouse. What you're doing is you're pumping a frequency, a bunch of force at a frequency into the antenna. And the idea is that the higher the frequency, the quicker it's happening. It really just is the speed of light argument, and that there's something less than, right, c happening in terms of the speed at which the force can go through the antenna. So if you have a very high frequency, the frequency, okay, there's not enough time between these little bits for it to go very far up the antenna. And so the only part of the antenna that can do this frequency thing is the part where there's enough time between the bits of the frequency. So the lower the frequency, the further up the antenna you can go. The longer the wavelength, the more time. The further up the antenna it has time to go to create your signal. And the quicker the frequency, the lower it goes. So microwaves have small antennas, radar, generally speaking, because the signal can't get through the antenna fast enough. There's not enough time. So the only part of the antenna that can create the right on-off signal is a tiny part of the antenna, where if you have a longer wavelength, then there's enough time to get all the way up the antenna to create the full on signal, the full length of the antenna. So radio waves have antenna polarization. You move the antenna, you can turn the signal on and off, just by having the antennas mismatched. And so for light, the difference is that the same truth exists in the sense that you're creating the frequency, though. So you're just putting regular energy in, even a DC voltage, and something else is causing the frequency. You're not providing the frequency for the light you create. So if you put electricity in a wire, you're not creating frequencies as high as the frequencies of light. And some other mechanism is taking the frequency you're putting in and multiplying it by having those frequencies jiggle something at half rates and then at quarter rates. So it's like creating two walls and bringing the walls together, and you end up creating a higher frequency, a higher vibration rate. So it's going in at one vibration rate, and the mechanism is amplifying it or doubling it or tripling it, or in some other way multiplying that vibration rate by causing reflections, like in the box. It's just like if the box has a certain rate at which arrows are going this way and arrows are going that way, and I make the box size smaller, you can sort of understand that the rate that they'll bounce is going to be increased by how small the box is. So anyway, the matter itself, the interaction between the electrons and the protons, moving towards and away from each other, and vice versa, is what's creating the medium, all right, that creates the mechanism that allows for the amplification of the frequency and eventually the movement out and the movement in of the crystals of the material. Yeah. That would be my draft analysis of some of the mechanisms that produce a photon. Obviously, there's a lot of little bits doing a lot of things, so there's a lot to diagram. But the truth is that they just haven't done any of that because they decided this is a mathematical system, and it's has something to do with some wave in, wave out, and no appreciation for how you have to turn what a wave would be, which is a wave of stuff, stuff coming at a frequency, on and off, push, no push, push, no push. And you're converting push, no push, push, no push into, the same thing on the other side. You're pushing one side and are pushing the inside and expanding the box by pushing pressure in. But that's all there really is, and that there has to be mechanisms that convert that frequency. And this sort of would explain why, different chemistry creates different frequencies. And the different chemistry has a different relationship between the electrons and the protons, and they will be able to vibrate at different speeds. Vibrate in the sense of move towards each other, move away from each other. Enough.
We can describe a photon in terms of how much energy it contains. We can describe a photon in terms of...
Let's just understand again, when they say how much energy it contains, the only kind of energy they pay any attention to, so all the energy for like gravity, they're not paying any attention to. That's not in the same realm. That's spent space. That's a whole different physics. And all the stuff that would be any kind of other vibrations that don't have to do with electrons creating voltage in a wire. So the only way they're measuring a photon is by measuring a voltage created by the polarization of the atoms in the material and the direction of force based on that polarization. As you change the polarization, you change which way the force is bouncing. Is it going this way, or is it going this way? Which way is it moving? They tend to move. And so all they're measuring is one specific kind of electron motion and calling that the definition of all energy in the universe, when it's not even close, I guess I would argue.
How long the wavelength is, we can describe a photon in terms of how we can deposit energy instantaneously onto an electron or.
So again, this depositing instantaneously. Now, it might be okay to say without losing any energy, but the real problem with that is they already know that light transmitting through materials takes time. The light is, in fact, slowed down, so to speak. So it's a long way from instantaneous. The light doesn't just hit the surface of the glass, go through the glass, and come out the other side at exactly the same speed it would have if it missed the glass. So it's a 40% difference, which is huge, kind of. It's half as fast. So instantaneous would be the wrong word, because we know this process isn't instantaneous. The conversion of the force from the bits moving to forming a kind of pressure, and the pressure's moving the electron, that all takes some time. And that's why transmitting light through a material takes time.
To an atom and distribute energy that way. It's the mediating particle between electromagnetic forces or for electromagnetic forces.
So he doesn't even know how to say that exactly, because he's basically saying that, yes, something like a photon is causing the pressure that causes magnets to move in different directions. Okay, so you're changing a field of pressure, and that photon is what we usually call the thing that we're imagining that's conveying from one object to the other object that you have to move. So one object is moving. They're saying a photon is telling the other object, some distance away, at the speed of light, the photon is conveying movement, because now this thing's position has changed. It's like me moving the mirror or me moving something in water. I'm changing its position. Therefore, I'm forcing whatever field is on the other side of me. See, the box would be in, a way of thinking about it is the box is in a box. Okay, the box is in the box of the universe, and if you expand the box, okay, one box, the little box is in this area, right? And so I'm going to pump energy into the box. I'm going to expand the box a bit. I can expand it in directions. Oh, sorry. But the trick is the box is essentially in the box that is the universe, and the universe is going to likewise have to change its dimensions. Its pressure is going to be changed. So if this box expands, that means there'll be more pressure going out in this direction. And you could be a box over here, and you're going to feel that movement, and the whole box itself is going to maintain the pressure. So there's always tension in the field. So you can think of it, like I said, if you want to call it an ether, go ahead. But the point is it's just something that can convey pressure. So whether you think of it as these little bits of BBs, like I said, if I had BBs and I bounced them all around inside of this box, right, they would have an equilibrium, okay, based on the size of the box here. And if I change the size of that box, then obviously those BBs are going to be bouncing into these surfaces back and forth at a faster rate because I changed the size of this box. So now I'm taking the pressure that was out here, I've pumped it into here. By pumping it into here, I've pressurized going out this way, and that's your equilibrium. It's going back into this box. But you can have layers of these boxes, obviously a galaxy and then a solar system, and these are all layers of box.
Versus we can describe a photon in many, many ways, but when it comes to trying to find a definitive size of it, it's very difficult to do. So
again, the standard for the size is the wavelength, the distance between what you'd say are the nodes or whatever. But that's essentially telling you how thick it is this way, because it's telling you over how much surface at the speed of light the same vibration can be manifest, essentially.
What I'm going to do instead of trying to talk about the the amplitude of the electromagnetic radiation waves in terms of the size of the photons. We're going to talk about it in terms of the size of the intensity of the electromagnetic radiation. And from that, I think we have a much better concept of what a photon is.
Right. I don't think it's a better concept at all. There's no description of the actual function. The fact that it is quantized, and that this is a field of soldiers, and you have to explain how you got the field of soldiers, a mass of soldiers. You just shoved a mass of soldiers in, and you're trying to explain why are they coming out in waves, okay, at a specific interval, and there's a whole mechanics that's causing that to happen, and they're just discounting it. They're just pretending, and we don't have to talk about that. And again, the whole point is that you have to sort of understand that there are produced over more than one atom, and that have to be received in the same way. That they can't just absorb. It can't be just one electron that's conveying the photon. Just as more than one has to produce it, more than one has to receive it.
For example, let's say we have a source of energy. It could be the sun, it could be a speaker, it could be anything that produces electromagnetic radiation. Well, a speaker would do that, but I would...
Yes, that's how they're so stuck in thinking of things happening in mediums that they just don't. I mean, it's kind of a critical thing. I mean, I'm not saying this is a big mistake or anything. I'm just saying that their whole view is so tied to thinking in terms of what happens in atomic type mediums, rather than understanding that on the smaller level, one step smaller than atoms, is this step where you have electrons and protons, and the fact that they are tied to each other based on the pressure between them, and that functions a little bit different in the sense that the rules are a little different because of their difference in their size and the fact that they're monopoles versus dipoles and a lot of other things. So it's enough of a difference that they should make that distinction, that when you're creating photons, you're doing something a little different than longer wavelength radiation.
Say maybe a radio broadcasting station or anything like that. And so the radiation then goes outward, and of course as it spreads out, it diminishes in intensity because intensity is proportional to, right here, is inversely proportional to the area over which the radiation spreads, so it's inversely proportional to r squared.
Right. So this is where they really start to cheat a lot of arguments. I didn't think there was that much in this video, but there's a lot of subjects here. So I've seen where they attempt. See, the r squared rule is a general rule. It's not a law. Okay, it's something that generally takes place because most things that are producing light are spherical or point sourced, in the sense that they're coming off some area that's not regular, that is regular. All right, so if the sun creates photons, it's creating it over its round surface. It tends to go round, and so the round surface is essentially creating the r squared rule, in the sense that as you double the radius, you quadruple the area of the circle, and so essentially at the bigger circle there would be 1/4 the amount of radiation per square inch, and so that's the inverse square law. What they're doing, you think about something like a laser beam, and you're saying, well, laser beams are doing something kind of different. Now, they're not perfectly parallel bits of energy, but they're clearly a lot more parallel than regular light, in the sense that they're not doing this thing anymore. Okay, they're not diverging dramatically. So a laser beam doesn't get weaker by the inverse square law unless you do something kind of cheaty, which is you say, instead of r being the distance, that is r being measured this way as distance, they're using r, to measure the divergence of the laser beam. So not until, so essentially this is what they're doing. They change it to a variable called w, and the w, the amount of divergence, tells them that at this point it's 4 times less, and than it would be at, say, this point, because that's double the W. So they're doubling the divergence. And of course, if you're doubling the divergence, you could do that with the sun too. You could just go to the point where I could just call it W and say, well, W happens to be right here where the divergence is going to be this much, how much the light has spread, and obviously that's going to create a square, and the square has an area, and this square has an area, and this one's going to be 4 times the area of that square. So they just cheat to say, oh yeah, no, a laser beam also obeys the inverse square law, when they've cheated, okay, by forgetting about the real cause and just defining it as, well, R just means the W. So it's only when the W is twice as much is there 4 times less laser light. But to make the W twice as big, you have to go miles and miles and miles. And so your R number would be preposterously high. So if you were doing the R squared, it wouldn't hold at all. So the law is completely violated by a laser beam. There's no inverse square law. And it's only through this perverse changing of the variable that you're able to contrive some notion of its existence. And the notion, again, just doesn't have anything to do with distance from the object. It just has to do with distance of the divergence. So they totally cheat to pretend photons are always obeying the law when they're not. So when he talks about the intensity of the photon, the real truth is, okay, it's just a simple argument that if it were bullets coming off the sun, you could understand that if I go twice as far away, the bullets are moving away from each other in both directions, okay, the square. So well, you can't quite see that. So if I'm hitting a square this big, the bullets would both be in the square, and there's a certain amount I'm going to get hit by. But if I make the square 4 times as big, obviously some squares don't have any bullets in them. I've made the likelihood of a bullet hitting me much lower, and that's the 4 times. The object gets, in a sense, as much as objects look like they get smaller with distance, in a sense the object's getting bigger and bigger, in the sense that it's spreading any amount of energy over fewer and fewer square inches of its body. It's one way of looking at it. Or you could just look at it the more obvious way. It gets harder and harder to hit the further away it is, when your bullets are coming out at angles. When they're moving away from each other, essentially, right? But they're not really moving away from each other.
Distance away from the source. Also, what we can think about it is in terms of electromagnetic radiation has wave-like properties where the electric field oscillations vary with position and time, and the magnetic field oscillations vary with position and time. And we know. So
you could say that these vary with time thing. These oscillations again have to be caused by something. You can't just say it oscillates like an electron. It's just sitting there, and they're going to say, "Oh, it moves this way, and then moves this way, and then moves this way." How does it know to stop, and how does it know to move back? It's not on a stick. And the stick is this energy, the force that's between these objects is the same force that photons are made out of. So there's energy, photons, moving it this way, and then energy, photons, have to move it back this way. It can't do it for free. And so it's obviously interacting with a system of boxes, a system of mechanisms that reflect pressure, and it takes and that pressure is bound, trapped, and so it's just going to end up reacting in the sense that it can't maintain the direction moving into pressure, so it's going to slow down and stop, and then it's going to move back the other way if it's going upstream, so to speak.
That those two are perpendicular to one another, so as the electric field oscillation changes in amplitude and direction like this, the magnetic field oscillations do the same in this.
So there's just no evidence that there's any of this, whatever that is. Okay, that there's two fields in the first place. that just happen to move exactly the same speed and be made out of whatever. Now, I would argue there are two forces, okay, but they're identical to each other in every respect, except they have this red shirt, blue shirt thing. They're swimmers, okay, going the speed of light. Some are wearing red shirts, some are wearing blue shirts. Blue shirts can get into blue boats, red shirts can get into red boats. Simple rules. None of this stuff. Nothing can do this. Nothing can go this way and stop and then go this way and stop unless there's a mechanism forcing it to do that. So that's just Newton's fundamental law. Something doesn't change until something acts on it to change it.
This direction perpendicular to one another. Of course, when we think about sunlight or radiation, we expect to see a non-polarized system. In other words, we expect to see the vibrations in all different directions, all 360 degrees. But let's.
So again, I don't know what he's implying. That all the photons have different polarization. That none of them have polarization. So the point would be is that when it's ejected by a crystal, it sort of just depends on how you're thinking about how the crystal's vibrating. Is it vibrating on its edge? And the edge is producing the light, or is it vibrating as a flat surface, producing, bits of stuff that flies off, and that stuff has a dimension to it in the sense that some of the stuff, one piece of stuff flew off here, one piece over here, and each time you're pushing, you push off a little bit different kind of stuff at different positions, and that collectively all of those soldiers are in line in the sense that so it's like I guess it would be like the soldier argument, except the soldiers don't have to all be in a row like a ray. They're in line, but they're not right in front of each other. So one can be here, and 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 then each time you're pushing the soldiers, they're in a different position in space. And that would be my argument of what mixed polarization would be. Because you haven't filtered them for something other polarization.
Keep it simple for now. We'll talk about that one later. Also, what we can see is that the Poynting vector of radiation, which means it is a cross product of the electric field oscillations, the magnetic field oscillations, times a constant, which is one.
So this is just more, kind of just mathematical gibberish. All he's really saying is we're arguing that this thing is moving pressure up and down, and it's moving pressure right and left. So magnetism is going this way, the magnetic field and electric field is going this way, and all we're saying is that the motion is in this direction. Okay, so the wave's moving this way. It's a moving wave. And that's all he's saying with the word Poynting vector. It's just saying there's no other dimension for it to move in. It can't move more in this direction. It can't move more in this direction. The only place to go is that direction. That's where this motions add up into motion in this direction, is kind of their argument.
1 over 2 mu sub naught. Now, the reason why that 2 is there, because we're taking the maximum value of the oscillations of the electric field and the magnetic field. If we take the RMS values, then we can get rid of the 2. So the intensity, which is equal to the absolute value of the Poynting vector, is equal to this. And since the relationship between the electric field oscillations and magnetic field oscillations is the speed of light, we can replace the magnetic field oscillations by E divided by C. And so we have a C here, and we make that E squared, E maximum squared. So the intensity of electromagnetic radiation can be described like this. And therefore, if you want to find the maximum...
So again, this formula would only work talking about a bunch, a million photons or a billion photons. Single photons don't lose their intensity. So one leaving from wherever, Alpha Centauri, a photon on its way, when it hits me here, okay, it's just as its intensity is 100%. It didn't lose something through the voyage. It's all still there. So they're just saying over a bunch of photons, the intensity is lost because they're diverging in their direction. They're not moving in perfectly straight lines, so they miss me at a distance. I mean, the closer I get, the more likely I'm going to get shot by the bullet, right? I mean, the closer I move, no matter where they shoot it, essentially, right? They shoot it this way, a little crooked, this way, a little crooked. Doesn't matter how crooked it is when I'm close enough, because they're going to hit me.
Of course, this is Emax. The electric field strength of electromagnetic radiation at any point in time, or at least the maximum at any point in time, which would be the maximum oscillation right here. We could find that by taking the square root of 2 mu sub naught c times
Right, so these are just averages, and they're just pointing out that no, there's a certain quanta of energy in the photon, and that's the maximum. It doesn't, there's no minimum and maximum. There's just what the photon is.
Let's do that for sunlight. What is it for sunlight? And that gives us an idea of how photons or how electromagnetic radiation actually works. So let's go ahead and put that in. Remember that mu sub naught is 4 pi times 10 to the minus 7 Webers per amp times meter. C is the speed of light. And I, in this case, for sunlight, I would be equal to 1,361 watts per square meter. So when we plug those numbers in there, this is equal to the square root of 2 mu sub naught, which is this number right here, times C, which is 3 times 10 to the 8 meters per second. And I would be 1,361 watts per square meter. And we get an Emax of, so we have 3 e to the 8 times 2 times pi times 4 e to the 7 minus and times 1,361. And then we take the square root of that.
So I think he means mu sub naught is mu 0, which, again, if you square these two things, the permittivity and the permeability of space, add them and square them, you get the speed of light. So that's why they're 2 in the square root thing. It's because they're just going back to that fact that if you combine what they're saying is the... See, they changed the definition of these constants because they never measured them, permittivity and permeability, and they've just changed them now, modern times, to the electrical constant and the magnetic constant. So they were always created numbers and created just for the purpose of making the math add up. And they basically subdivided what I would argue is one force, electricity and magnetism. The electric field and the magnetic field is just one field. And kind of the evidence of that is their mathematical equations are using a subdivision of the speed of light. They've bisected the speed of light into two constants and given them electric and magnetic priority. And that's just an illustration that they're really talking about one force moving at the speed of light, not two forces moving at some subdivision of the speed of light. So essentially, as long as they put both fields into their math, they'll end up with, one will be doing 0 and one will be doing something. So when they're talking about magnetism, the magnetic field is the whole component, and then we have the electric field for the purpose of use of knotting, putting the other half of the speed of light into the equation.
And we get, well, let me put on my glasses because I'm having trouble finding the decimal point, 1,013. And of course that would be volts per meter or newtons per coulomb. So when sunlight reaches us, of course we can understand that sunlight consists of a myriad of photons. When it reaches us, the electric field oscillations vary from 0 to a maximum of 1,013 volts per meter. That means the potential difference over a distance of a meter is 1,013 volts. Okay, we'll get to that in just a moment. Now also we can describe the electric field oscillations as a wave function.
So turning volts into distances, again, it's just talking about how far the light travels at the speed of light. So it just doesn't really mean much.
A wave function that diminishes over distance. So the electric field oscillations will drop off as a function of distance, but since intensity is that wave function squared, then of course we can see that this would be E squared over R squared, and therefore we can see that the intensity drops off as 1 over R squared. The equation is, of course, the electric field oscillation strength divided by the distance times the cosine of Kr minus omega t, and that is a standard format of a wave equation. This determines the strength as a function of position. This determines the strength as a function of frequency. And of course, remember that the speed of the wave is equal to omega over k. And of course, omega over k can be written as 2 pi f over 2 pi over lambda. So you can see that c, the speed of light, is equal to the frequency times the wavelength.
Right, I see the W in here now. So this is dangerous. So now they're talking about the divergence and making the equation a divergence equation when it's not spherical. So you could sort of argue that they do this with antenna radiation. Instead of measuring the actual distance it travels, they're using the distance of the wavelength and the amount of divergence as a substitute for the inverse square law. And so they're not really talking about absolute distances. Because one could argue that radio waves aren't diverging in both directions as much. They're diverging in one direction. The antenna is sending beams that are diverging off the antenna in different directions. Those are diverging that way, but it's not really diverging as much this way. So it's not exactly a square rule.
And so there's the equation for the oscillation of the electric field. If we square that, we know the intensity is proportional to that, and therefore we can see that it drops off as 1 over r squared. Now, here's the real key here. As sunlight...
So it doesn't drop off as 1 over r squared in the sense that it depends on what's radiating the force. It doesn't in a laser beam. And it probably likely doesn't in, when you have like a dish antenna and you're concentrating the photons.
It moves through space at the speed of light, and it then encounters an electron. So let's draw that up. So let's say here we have the sunlight that is moving from left to right, and here is an electron. As the sunlight is moving past the electron will experience an electric field, but a changing electric field, an electric field that will change from 0 to a positive 1,013 volts per meter, from 0 to a negative 1,013 volts per meter, and back and forth. So when the electron experiences the positive volts per meter, of course, remember, if there's an electric field, and let's say the electric field is at this moment directed like this. So there's electric field, and of course that means that there's a seemingly positive charge on this side and negative charge on this side. So at that very moment, the electron will feel a force caused by the electric field being in that direction at that moment at a certain magnitude.
So again, this is kind of easy to argue that they know that isn't how it happens because the polarization of the photon is gigantic compared to the size of an electron, and it would be moving all the electrons, millions of electrons with one photon. They know that the photon doesn't have the energy to move millions of electrons. So this is where their story just becomes a story, where they're just giving you something like, and instead of, it could be something like, instead of saying that, they're saying it as if they know this is how it works, that the electron is sensing some sort of negative field. It's sensing the pressure it's in, and you're adding pressure to the box, and the box is changing its shape, and as that box changes its shape, the other boxes change their shape, and that's what's really happening.
And the electron will feel...
really happening in better metaphor, than this story. It's more accurate to say that the pressure you're putting in will have effects on how the relationship between the electrons and the protons, and that expanded relationship will expand the atoms, and by expanding the atoms you're expanding the substance, and by expanding the substance you're changing what it's doing to the external universe. Making it bigger and smaller, bigger and smaller, bigger and smaller means it's going to reflect light to the rest of the universe bigger and smaller.
Force in this direction. But since the electric field oscillates at an enormous frequency of about 600 trillion times, trillion times per second, then very, very soon after that, the electric...
So some sort of notion that this frequency, that's very fast, could equal anything but a tiny bit of motion in an electron. That's the tiniest bit, trillions of times a second it's going back and forth. But what's really happening is getting hit by stuff that's happening a trillion times a second. So it's getting pushed a trillion times a second, and it's moving back a trillion times a second.
The field will be directed in the opposite direction as it's moving back and forth. The electric field goes up and down like that. At that moment, the electron will feel a force in the opposite direction. And so you can see...
feel a force in the opposite direction. Yes, it will be forced by the pressure of the system. The system says you pushed me, and it's going to push back essentially. And that's all there's going to be. It's just pressure inside of pressure, inside of pressure, inside of pressure. And you can't push on anything without changing the pressure. And if you change the pressure, you push the two ping pong paddles together, it increases the amount of pressure between the two paddles, and they move apart. It's that simple.
The interaction happens between an electric field, oscillation caused by, of course, electromagnetic radiation traveling past an electron, it will feel a force going up and down or left and right or at any particular angle depending upon the direction of the electric field oscillations. So that's how electrons feel the effect of electromagnetic radiation, because it's fast oscillating electric field. So we can't really talk about the amplitude.
So again, it almost defies your reasoning skills to say that, okay, I'm moving something up and down and forward, and somehow that's only going to move the electron up and down. It's not going to move it forward. So it sort of breaks continuity, just giving this thing more potential than it really has. It can't be doing this and doing this. And what the force is really doing is it's moving in one direction. It's going to impose momentum in one direction. And that one direction can be converted by the processes of electrons and protons. They can make it turn right or turn left. But you can't have two momentums at the same time, if you get what I'm saying, right? You can't impose a momentum this way and a momentum this way at the same time unless you were traveling this way. And we know the photon's not traveling this way. We know it's going from point A to point B. And that's the direction of the initial momentum. And that's the likely direction of the momentum that will leave the box.
Of the waves. So when we take a look at E over R, that's not really the amplitude of the photon, which would reveal something about the size. Rather, it's about the strength of the photon, or the effect that it will have on charged particles.
So he's just turning something, like I said, he's turning something that's clearly moving in a direction with a perpetual energy. And he's attempting to explain why its energy decreases over time by ignoring the fact that he was sent with a bunch of other soldiers. He's pretending the soldier got tired. You know, the one soldier ran out of energy. And that's not what happens over distance. What happens over distance when I send a bunch of soldiers going in all directions is that the likelihood of the soldiers hitting one place in space gets less and less as I get further away. I'm less likely to get a soldier here. The soldier's still moving with the same energy and same intensity. They're just spread over a larger area. And that's the inverse square law, and he's trying to pervert it into some kind of equation that says photons actually lose energy when they don't.
Particles by the amplitude of the electric field oscillations. So photons don't really have an amplitude like we typically see in a wave, like an ocean wave or a wave on a string, but it has an amplitude in terms of the strength of the signal. And that's then repeat.
So again, I'm just pointing out how that's just absolutely nonsense. They have one strength, it's their momentum. Their momentum is always the same, and all you can do is spread the momentum over a larger area. And that's the only way you can diminish the intensity of a photon, is to diminish the number of them hitting you.
In terms of the strength of the electric field oscillations as the electromagnetic radiation moves from left to right. And it's the strength of the varying strength of the electric field strength that causes the electrons or protons or any charged particle to feel the effect of that. The farther out you go, the weaker the field will get, because the bigger R, the smaller the ratio of E over R, then the...
Yes, and it's only the collective field. So again, this is pretty bad to imply that the individual photons are losing amplitude, when all he's really saying is the number of photons that will be waving that electron. The number of them decreases. The number that will be affecting a bunch of electrons, not just one electron.
Strength of the electric field oscillation will diminish, and therefore the effect of charged particles will diminish as you go farther out. So, can we talk about...
No, you'll affect fewer and fewer electrons the further away you go. The further away I move from a light source, the fewer photons that hit fewer electrons, period.
About photons in terms of the size of the amplitude? No, we can't. So we can't talk about photons in terms of the change in the electric field as the photons move along, and that strength of that change of the strength, the amplitude of the oscillation of the electric field, is really what we can talk about in terms of photons.
Well, you're really not talking about it. You're not explaining how the collection of photons are collectively moving the field, because it really has to be a collective accomplishment in the end. For our eyes to receive photons, we need 9 of them, 6 or 9, whatever the right answer is. So this is just it's not accurate. Yeah, that much I can say. I guess we'll pause. An apology from the electric utility. Yeah. I mean, really, we have no civilization. I mean, that's so easy to stop. I mean, our government can certainly stop it. They don't. These people are making money. That's all that matters.
So hopefully that helps us understand photons just a little bit better. That's how we do it.
I mean, a perfect use for drones, really. Drone them. Anyway. So, yeah, this unaccountable thing. Yeah, oh yeah, it's really cool being unaccountable. This is what you get. A bunch of people who want to run away from accountability. So anyway, enough. Done my job. Until next time and such. Yeah. That's all. Pretty sure. Sure enough.